Let's say if I showed you a few dots on a plane and asked you to divide the dots into clusters. Let's say if I showed you this graph and asked you to divide the data into two clusters. It wouldn't be that hard. Now if I ask you to divide the same clusters, or let's say if I asked you to divide the same data set into four clusters, it wouldn't take as long as well. But let's say if I had a data set that was quite large and it was more than 2 dimensions, or let's say if it was more than 3 dimensions, and you had to find k number of clusters, let's say 16 or 17 or any number for that matter, it wouldn't be as easy for a human to do that. We'd need computers to come in and help us. Although it is not easy for a computer to do that as well, it would be much better than a human. K-means clustering is one such way for us to do that. It helps us divide a data set of say n size, and let's say in d dimensions, where n and d could be any numbers, into k number of clusters where k can also be any number. It's a quite common and quite popular unsupervised machine learning algorithm. It's commonly known to be NP-hard, which basically means that you cannot solve the problem in less than exponential time complexity. But you can, however, verify it. Unlike NP problems, you can verify if the problem has been solved in n complexity, or polynomial at the very least. And that basically means it's not as easy for a computer to solve the problems of an unspecified number of dimensions, an unspecified number of clusters with an unspecified size. Now the coding part is not as complex. We'll be using Jupyter notebooks with Python, but you can use R or any other programming language for that matter. We'll be using pandas and matplotlib to basically read and visualize the data respectively, and we'll be using a few functions from NumPy. However, you don't need NumPy for any matter, and for that matter you don't even need pandas or matplotlib if you don't want to visualize the data or read the data from the CSV into a data frame. But you would basically follow the same logic regardless of their language, regardless of how you've read the data or the type of data structure that you're using to store the data. The steps would remain the same. So let's get into the programming part. So k-means clustering. Basically, we're using 3 libraries. I imported the fourth just to show to you that you could also use SNS, Seaborn, for the plotting part. NP, I'm only using 2 functions, which are mean and square root. Pandas is for the data frame, and we're reading a CSV. So we imported pandas. We have NumPy, pandas, matplotlib, and Seaborn. You can do work without all of them, and k-means doesn't require you to use either. It's just for simplicity and readability that I imported some libraries. So to read a file, we simply use pd.read CSV. The IRCSV has data about petals or petals of flowers, and I have links of it down in the description if you want to download it. .head simply shows us the first 5 entries, and let us run some of the cells. Now this one. So this is the general data of the data set. We don't want to use the species column because it has categorical data. We would rather use petal width, petal length, sepal width, and sepal length. So we make a copy of the data frame and drop the species column. Alright. In place means simply we're removing it in the actual array and not making a copy and returning it. So once we have done that, we'll make sure that we have all of the columns as floats and we haven't read them as objects or strings. We'll make sure, see, we have integers. Now this is the actual coding part. Firstly, I have defined a function to find the distance of each of 2 points. So the formula of finding the distance would simply be the square root of the sum of all of the points of the data point. So if the data point is simply one dimensional, then you'd simply subtract the midpoint from the actual value. If it isn't, then you have to subtract all of the components of the vector. So that is why I've used np.sum and I haven't used simple sum, because it could be possibly a vector. We are subtracting 2 vectors. The result would also be a vector. We're taking the square of those vectors and then we're summing them together, and then we're taking the square root. The squaring and the summing was to make sure that we drop the negatives. Once we've done that, we'll do all of the steps that we have described earlier. Step 1, select 2 random points or n or k random points from the data set, k being the number of clusters that we want. We make k number of empty clusters to store our clusters, list of clusters to store our clusters. This is a list comprehension in case you haven't seen it before. There are easier ways. There are an easier way of writing for loops for appending data. So I've written 2 different types of functions. One is specifically for the data frame, and the rest is for everything else, because data frames have specific functions that others don't have, and certain things that don't work for data frames. So for instance, if you wanted to get ith entry from a simple list, you would simply provide data extraction I. But if you wanted it from an data frame, you need to use the location function. So let's get back to the steps. Step 1, we find k number of random points. We find the distance of each point in the data set from the centroids. See, Euclidean distance, and we're storing the distances in a list. Then we find the minimum of that list, whichever value is the minimum, and then we check which index that value is at. Alright, then we append it to the list, and if our new centroids equal the old centroids, we break the for loop, and we find the mean to store our new centroids. Apologies, the camera just went on. So we're on the step 4. If we get the old centroids once again, then we break our loop. If not, we find the new centroids by calculating the mean of the clusters, and otherwise, if we don't have a data frame, then we do the exact same thing. The only difference would be that we wouldn't use the log function, we would simply get the data, and we wouldn't append each element, or we wouldn't append an array of elements, we would simply append an element. Alright, so other than that, it would be the exact same function. Let's just simply run it. Ran fine, no errors. Now I return the values, the clusters, into a clusters variable, centroids into centroids, but this one was for a single dimensional array. It worked perfectly. But you could also pass in data frames or vectors, which I did here. Remember, we made this using removing the last column, or this last series. We get the return of that into multi-clusters, and we get the centroids in this. I've simply used 3 colors and markers to make sure that we see the clusters clearly. The data we have returned is in form of lists of lists, so we have to convert it into data frames. So for each cluster, I append a data frame of that cluster into our list. Alright, and this is just to make sure we have the same columns as our data. Alright, now we plot the clusters, and I've also plotted the original to make sure we aren't doing any data manipulation. So let's see. The output we get is 3 clusters and the actual data. Now, you might be thinking that these aren't clusters, they are overlapping. Well, in reality, they aren't overlapping because this data that we have plotted is in 2 dimensions. However, the data that we passed in was in 4 dimensions. So it's like putting my hands in front of my hand and saying that they are overlapping, but in reality, they aren't. Because in 3 dimensions, the third dimension is what they're differing on. So even though they look like they're on top, they aren't, right? Similar on this. And another thing, if I run this function again, we'd get different clusters. See, the clusters are different, and if I run it once again, I would once again get different clusters. That's simply because each time we run the k-means functions, it gives us, we start with a random point in the cluster as the center of the cluster, and we stop the iterations once we get the same cluster centroid again. But every time we run it, we have a different center as a start, so it would give us different results. One way of fixing this would be to run the k function over and over again until we get a cluster which has until we get a cluster set which has equal values in all sets. So yeah, other than that, that was it. You could also have used SNS to plot the data, but I used Matplotlib instead. So thanks for watching the video. I hope you liked it. See you next time.